Paramagnetism is a form of magnetism whereby certain materials are attracted by an externally applied magnetic field and form internal induced magnetic field in the direction of the applied magnetic field. In contrast with this behavior, diamagnetic materials are repelled by magnetic fields and form induced magnetic fields in the direction opposite to that of the applied magnetic field. Paramagnetic materials include most chemical elements and some compounds. They have a relative magnetic permeability greater than or equal to 1. It explains a positive magnetic susceptibility and hence are attracted to magnetic fields. The magnetic moment induced by the applied field is linear in a field strength and rather weak. It typically requires a sensitive analytical balance to detect the effect, and modern measurements on paramagnetic materials are often conducted with a squared magnetometer. Paramagnetic materials have a small positive susceptibility to magnetic fields. These materials are slightly attracted by a magnetic field, and materials do not retain the magnetic properties when the external field is removed. Paramagnetic properties are due to the presence of some unpaired electrons and from the realignment of the electron paths caused by external magnetic field. Paramagnetic materials include magnesium, molybdenum, lithium and tantalum. Unlike ferromagnets, paramagnets do not retain any magnetization in absence of an externally applied magnetic field because thermal motion randomizes the spin orientations. Some paramagnetic materials retain spin disorder even at absolute zero, meaning they are paramagnetic in the ground state. It explains in the presence of thermal motion. Thus, the total magnetization drops to zero when the applied magnetic field is removed. Even in the presence of the field, there is only a small induced magnetization because only a fraction of the spins will be oriented by the field. This fraction is proportional to the field strength, and this explains the linear dependency. The attraction experienced by ferromagnetic materials is non-linear and much stronger so that it is easily observed. For instance, in the attraction between a refrigerator magnet and the iron of the refrigerator itself. Constituent atoms or molecules of paramagnetic materials have permanent magnetic moments. Even in the absence of an applied field, the permanent moment generally is due to the spin of unpaired electrons in atomic or molecular electron orbitals. In pure paramagnetism, the dipoles do not interact with one another and are randomly oriented in the absence of an external field due to the thermal agitation resulting in zero net magnetic moment. When a magnetic field is applied, the dipoles will tend to align with the applied field, resulting in a net magnetic moment in the direction of the applied field. In the classical description, this alignment can be understood to occur due to a torque being provided on the magnetic moments by an applied field, which tries to align the dipoles parallel to the applied field. However, the true origin of the alignment can only be understood via the quantum mechanical properties of spin and angular momentum. If there is sufficient energy exchange between neighboring dipoles, they will interact and may spontaneously align or anti-align and form magnetic domain, resulting in ferromagnetism or antiferromagnetism respectively. Paramagnetic materials that are above their Curie temperature and in antiferromagnets above their Néel temperature. At these temperatures, the available thermal energy simply overcomes the interaction energy between the spins. In general, paramagnetic effects are quite small. The magnetic susceptibility is of the order of 10 raised to power minus 3 to 10 raised to power minus 5 for most paramagnets, but may be as high as 10 raised to power minus 1 for synthetic paramagnets such as ferrofluids. In conductive materials, the electrons are delocalized, that is, they travel through the solid more or less as an electron gas. Conductivity can be understood in a band structure picture as arising from the incomplete filling of energy bands. In an ordinary non-magnetic conductor, the conduction band, when a magnetic field is applied, the conduction band splits apart into a spin up and a spin down band due to the difference in magnetic potential energy for spin up and spin down electrons. Since the Fermi level must be identical for both bands, this means that there will be a small surplus of the type of spin in the band that moved downwards. This effect is a weak form of paramagnetism known as polyparamagnetism. The effect always competes with a diamagnetic response of opposite sign due to all the core electrons of the atoms. Stronger forms of magnetism usually require localized rather than itinerant electrons. However, in some cases, a band structure can result in which there are two delocalized subbands with states of opposite spins that have different energies. If one subband preferentially filled over the other, one can have itinerant ferromagnetic order. This situation usually only occurs in relatively narrow bands which are poorly delocalized. After studying this module, you shall be able to know about paramagnetism and its origin. Learn about orbital magnetic moment and spin magnetic moment. Identify the effect of temperature on paramagnetic materials using Curie's law and Curie West Law. Evaluate the Curie and Néel temperature for different magnetic materials.
Introduction to Paramagnetism. Paramagnetism refers to the magnetic state of an atom with one or more unpaired electrons. The unpaired electrons are attracted by a magnetic field due to the electron's magnetic dipole moments. Thus, in paramagnetism, the atoms or molecules of the substance have net orbital or spin magnetic moments that are capable of being aligned in the direction of the applied field. Paramagnetism occurs only in the presence of an externally applied magnetic field. Paramagnetic materials are attracted by magnetic fields and hence have a relative magnetic permeability greater than or equal to 1. The magnetic moment induced by the applied field is linear in the field strength and rather weak. Sources of paramagnetism. An electron has two motion associated with it. First, it's going around the nucleus in an orbit. Since the electron itself is charged, this orbital motion is equivalent to the movement of a charge along a loop, which generates a magnetic field perpendicular to the plane of the orbit. Thus, the movement resulting from electron orbiting the nucleus is the orbital magnetic moment, which is denoted by mu L. Second, other motion is the spinning of electron about its own axis, which too is equivalent to the movement of a charge and generates a magnetic field. The magnetic moment resulting from electron spin is denoted as mu s and is called the spin magnetic moment. Orbital magnetic moment. Let us assume that a single electron of charge E and mass m is moving about a nucleus O with an average angular velocity omega. The number of revolutions per second the electron makes is then omega upon 2 pi. The current it carries per second is E omega upon 2 pi ESU, that is equals to E omega upon 2 pi c EMU. According to the principles of electrodynamics, such an orbiting charge generates a magnetic field whose moment is given by orbital magnetic moment mu is equals to strength of current I into area of the orbit A. Then mu becomes equals to E omega upon 2 pi c into pi r square, which becomes E omega r square upon 2c, where c is the velocity of light and r square is the mean square radius of the orbit. Such a relation has little utility if it cannot be expressed in the form that includes the quantum number characteristic of the electron moment. An electron has characteristic angular momentum which is expressed as orbital angular momentum quantum number L. As we know, orbital angular momentum m omega r square is equals to under root L plus 1 into h upon 2 pi, where h is the Planck constant. So, the orbital angular momentum mu L is given by E omega r square upon 2c is equals to under root L into L plus 1 into EH upon 4 pi mc, which is again equals to under root L plus 1 beta, where beta is the Bohr magneton unit of magnetic moment and its magnitude is given by beta is equals to EH upon 4 pi mc is equals to 0.917 into 10 raised to power minus 20 erg Oersted. Spin magnetic moment. As we can see, the ratio of orbital magnetic moment E omega r square upon 2c and orbital angular momentum m omega r square is E upon 2 mc. For spinning electron, the ratio of spin magnetic moment and spin angular momentum is E upon mc. Therefore, we can write spin magnetic moment mu s is equals to spin angular momentum into E upon mc. Mu s is equals to under root s plus 1 into h upon 2 pi into E upon mc and becomes mu s is equals to 2 under root s plus 1 eh upon 4 pi mc, which becomes equals to 2 under root s plus 1 beta, where s stands for the spin quantum number. This is called spin only formula. For any system, s is equals to n into 1 by 2 is equals to n by 2, where n is the number of unpaired electrons. Hence, μs is equals to under root 4 into n by 2 into n by 2 plus 1 beta. Orbital angular momentum mu L and spin magnetic moment mu S are often written as mu L is equals to g under root L plus 1 beta, where g is equals to 1, mu S is equals to g under root s plus 1 beta, where g is equals to 2, where g represents the gyromagnetic ratio, the ratio of spin magnetic moment to the spin angular momentum. The magnetic moment of an atom is obtained from the sum of orbital magnetic moments and spin magnetic moments from all of the electrons in the atom. Some atoms will have a total magnetic moment and others will not. For multi-electron system, capital L is equals to small l1 plus small l2 plus small l3 plus so on, and capital S is equals to small s1 plus small s2 plus small s3 plus so on. So the total magnetic moment of an atom becomes mu L plus S is equals to under root 4 s plus 1 plus L plus 1 beta. Paramagnetism and temperature. The classical theory of paramagnetism was developed by Langevin on the assumptions that each atom is a little permanent magnet, and these atomic magnets tend to line up parallel to an applied magnetic field. But the alignment is resisted by the thermal agitation of the atoms. There is an obvious identification of the hypothetical atomic magnets with the magnetic moments induced by orbital electronic motion. Langevin deduced the following expression for the molar paramagnetism: chi m is equals to n mu square upon 3kT, where n is the Avogadro's number, mu is the permanent moment, k the Boltzmann constant, and T is the absolute temperature. A precise expression will also include a term for relatively small diamagnetic part of the susceptibility. In case of paramagnetism, chi m is inversely proportional to the absolute temperature. However, in the case of diamagnetism, chi m is independent of the absolute temperature. This theoretical prediction is fulfilled experimentally for a very large number of substances. Mu is expressed in EMU in previous equation, but more popularly, mu is expressed in Bohr magneton Bm. So the equation becomes chi m is equals to n mu square beta square upon 3kT. On rearranging this equation gives magnetic moment mu is equals to under root 3k into chi m into T upon n beta square, which becomes equals to 2.83 under root chi m T Bohr magnetons. Now let us find out the unit of beta means Bohr magneton and mu in CGS system. As we know, beta is equals to EH upon 4 pi mc, where E is expressed in centimeter raised to power 3 by 2, gram raised to power half per second, and H in centimeter square gram per second, M in gram, and C in centimeter per second. So putting all these units in the formula of beta, unit of beta becomes equals to gram raised to power half, centimeter raised to power 5 by 2 per second. And as we know, erg is equals to gram centimeter square per second square. So the unit of beta in form of erg is equals to erg raised to power half centimeter raised to power 3 by 2, which becomes equals to erg per Gauss. Now, as we know that mu is equals to under root 3k chi m into T divided by n beta square Bohr magneton, where chi m is expressed in centimeter cube per mole, K in erg per Kelvin, N in per mole, and temperature in Kelvin. So the unit of mu is equals to erg per Gauss, which becomes equals to Bohr magneton. Thus, mu is not a number and it is not dimensionless. Curie's law, the magnetic susceptibility equation, may be expressed in the form chi is equals to C upon T. The relation is known as Curie's law, where C is the Curie's constant and is characteristic of a paramagnetic substance. The constant C is given by the Langevins expression C is equals to n mu square upon 3k, where n is the Avogadro's number, k is the Boltzmann constant. It may be noted that if magnetic susceptibility obeys the Curie's law, then magnetic moment is independent of temperature. Thus, a plot of 1 upon chi versus t should give a straight line of slope 1 by c passing through the origin. This expression is approximately true for many solids, liquids, as well as for at least one of the two common paramagnetic gases, oxygen and nitric oxide. Curie's law is exhibited only A when the magnetic susceptibility arises entirely from the ground state and there are no thermally accessible states. B. When the magnetic dipoles are completely independent of one another. Among the ideal Curie paramagnets are diammonium manganese sulfate, potassium chromium sulfate, and ganodium sulfate. Unfortunately, it has been observed that more accurate magnetic measurements lead to greater deviations from Curie's law are discovered. For many systems, a plot of 1 by chi versus t gives a straight line, but intercept is non-zero on the temperature axis. These systems do not follow Curie's law due to the following reasons. A. There is some cooperative interaction between the neighboring dipoles, or B. There are energy levels whose population changes with variation in the temperature, or C. The applied magnetic field induces some temperature independent paramagnetism. Curie West Law. For such system, Weiss obtained following expression theoretically by considering mutual interaction of the elementary magnets or molecular magnetic fields. Chi is equals to C upon T minus theta. This relation is termed as Curie West Law, where theta is referred to as the molecular field constant or West constant, and C is called Curie's constant. The West constant take care of the cooperative interaction. Theta correct the temperature for non-zero intercept describes the so-called Curie West behavior. It is common to have non-zero intercept in the systems that are non-magnetically dilute. It explains pure solid paramagnetic materials. In these systems, interionic or intermolecular interactions cause neighboring magnetic moments to become aligned and contribute to the value of intercept. For ferromagnetic substance, theta is positive. It explains theta is greater than 0. Whereas antiferromagnetic substances, theta is negative. It explains theta is lower than 0. The magnitude and sign of theta can be obtained from a plot of 1 upon chi versus t. Theta is replaced by the term Tc, Curie's temperature for ferromagnetic substances. When ferromagnetic substances are heated beyond Curie temperature, they become paramagnetic. Curie temperature for Fe, cobalt, nickel and gadolinium are 770 degrees Celsius, 1121 degrees Celsius, 358 degrees Celsius and 44 degrees Celsius respectively. For antiferromagnetic substances, theta becomes Tn, Nil temperature. Chi reaches a maximum value at Nil temperature and then decreases with further fall in temperature. Therefore, a plot of 1 by chi versus T should show a minimum at Tn. So the antiferromagnetic substances, when heated beyond Nil temperature, become paramagnetic. In ferromagnetic substances, within a certain temperature range, there are net atomic magnetic moments which line up in such a way that magnetization persists after removal of the applied field. Above the Curie point, thermal motion is sufficient to offset the aligning force and material becomes paramagnetic. Antiferromagnetic materials exhibit antiferromagnetism at a low temperature and become disordered above a certain temperature. The transition temperature is called the Nil point. Above the Nil point, the material is typically paramagnetic. Sometimes theta have got negative value, but the material do not show antiferromagnetic coupling. Therefore, a negative value of theta need not always implies an antiferromagnetic coupling. For example, titanium, cesium, alum obeys the Curie West law above 200 Kelvin with theta is equals to minus 200 Kelvin. When the temperature is lowered further, chi is leveled off to a constant value. This high negative value of theta cannot be assumed to mean a strong antiferromagnetic coupling because a. The magnetic susceptibility versus T curve does not reveal the usual maximum. It explains Tn, the Nil temperature. B. The magnetic susceptibility determined experimentally does not fit the theoretical equation for antiferromagnetism. When theta is taken from the 1 by chi versus t plot, the magnetic moment should be calculated using relation mu is equals to 2.83 under root chi m t minus theta Bohr magnetons. Many paramagnetic coordination complexes exhibit theta value close to 0. Therefore, we neglect theta and calculate the magnetic moment. It could not give appropriate value of mu.
In this module, we discussed the two sources of paramagnetism are an orbiting electron and a spinning electron. The moment resulting from the orbiting electron is the orbital magnetic moment denoted by mu L. The magnetic moment resulting from electron spin is denoted as mu s and is called the spin magnetic moment. Curie's law states that the magnetic susceptibility of paramagnetic material is inversely proportional to the temperature. For the systems which do not follow Curie's law, West obtained an expression theoretically by consideration of the mutual interaction of the elementary magnets or molecular magnetic fields. This relation is termed as Curie West Law. Curie West Law explains the behavior of ferromagnetic and antiferromagnetic substances.